So last day we have just completed the different type of parser. So if we go back to the stage that we have seen at the very beginning of this course, that we have lexical analysis step, then syntax analysis step. So these two part is completed at least, and now we are in the phase of this third stage, that is semantic analysis. So if you can recall what I told you about the syntax analysis output, that is it's basically give you a parse tree, right? Now the parse tree does not satisfy some constraint. For example, if you can recall, I told you that for example, if there is a grammar a to say b plus c, and what does this mean? That whatever value of b and whatever value of c will be added, right? And this addition is only possible if both v and c are of same data type, at least in a very simple case. If we consider, I mean, at least if b is an integer, c cannot be float, I mean, sorry, cannot be a character, at least, right? So this checking whether both, whether the uh, data type of the terminals are correct or not, that is not possible to check by this syntax analysis phase. Syntax analysis phase only check that whether the string that is input to the compiler, that is syntactically correct or not. That means, is there any way to form a parse tree from the string as well as using the production rules? And if it is so, then it will pass the syntax analysis phase. But technically, if I say that the value present in b, that is an integer, and value present in c, that is a character, you will say it's not possible to add. And this checking is done in this semantic analysis phase. Okay, so basically that means if I simply tell you in a very in a single line that what is the output of this semantic analysis phase, let's draw a very simple diagram over here just to recall what actually is there. Suppose we have a black box here, which was your syntax analysis phase, and there has to have another black box that represents the semantic analysis phase, right? So maybe this is your syntax analysis phase, and this will be your semantic analysis phase. So, and this input of this syntax analysis phase is what it is: stream of tokens that is coming from the lexical analysis part, right? And the output of the syntax analysis that becomes the input of the semantic analysis is the, what you can say, parse tree. Now question is that how a tree can be an input to another phase, right? That can be a question. Remember one thing, that what we are talking about parse tree is nothing but, actually, for example, if I give you a simple simple example here, that say for example we have a grammar something like e to e plus t, or maybe t, or maybe e multiplied by t. Okay, or can be okay, do one thing, not t, let's take e to e plus c, e plus t. um, okay, no, it's better to keep t over here, so let's t, or maybe t, and finally t will be written as some identifier. Okay, so with this particular grammar, if I say for example, okay, let's don't consider id, let's consider we have a possibility it will be either a or b or c. So that means from this grammar I can say that at least I can draw any mathematical formulation including plus and star and a b c as a terminal string, right? So a possible string can be something like, for example, a plus b multiplied c, right? Now you may tell that this is a left recursive grammar, so definitely a parser not possible to design, that we know. But you know, just for timing, this since we are not exactly trying to design any parser here, just forget about this constraint for instance, and try to understand the philosophy that I am trying to say. That is that using this production rule, you set up production rules. If I ask you that just somehow check whether this string is syntactically correct or not, so what basically you will say, that let's try to draw a parse tree, right? And what will be the parse tree? It can be something like e to say e plus e plus no, e star t, e star t, this will be again I can written as e plus t, and this e can be written as t, then it can be written as a, and this t can be written as b, and this t can be written as c, right? So using this production, using this syntax tree, if you start from the beginning, like start from the beginning, you start from the root and you go downward in this way. Okay, you go downward in this way, when you will see that there is a leaf node, you will start going back. So basically what you are doing, you are actually reducing this small a terminal string to a variable, right? So that means the first rule that you have to use to generate this parse tree, you can say that, okay, for the rule number one, not rule number one, the first, in the first step you have to reduce this a to capital T using which production rule? Obviously the production rule t to a, right? So that means the first production rule that will be used is t to a. Then next one, you see we are going upward in this way, and now this t is reduced to capital E, right? So that means the second one that is required is e to capital T, this particular production rule. Then I will go upward again and I will see that there is nothing to go, and then still again I will go downward, seeing it is plus, nothing to do, I have nothing to reduce right now. You see, then again I will get a leaf node and I will start reducing. So you see that when I'm going upward, it's what we call reduction. And this word reduction already we have seen many times in designing previous parsers, right? So basically here that is why you see this reduction is so important. Okay. So at least when you will start reducing, then your the parse tree will be not parse tree will be generated. I should say that what should be the production rule that I should use, that will come into the picture. So here now next time, in the third step, we have to use T to B, this production rule, to reduce this small b to capital T, just opposite one. Reduction means the opposite one, small b to capital T. But exactly what production you are using? T to B, right? Okay. So then I'll go upward again, and you will see that everything is done, reduced over here. Now you can apply in the fourth step, you can apply E to E plus T. Right, E to E plus T, and then I'll go upward again, and like this, and I'll go, and then again I'll get a leaf node, I'll start reducing it again, and it's now reduced small c to capital T. That means the fifth one will be capital T to C, and then it will go upward again, and I'll finally reach to root, and then I can easily understand, I hope you can easily understand that the sixth one will be nothing but E to E star T, right? So you see, that mean what basically we have, what knowledge actually we have gathered from this sparse tree, that is, among all these production rules, among all these production rules, which production rules has to use in which order to generate this particular string that is presented over here. That is the main purpose of parse tree. So basically what we are saying, that this syntax analysis is sending, is giving the output parse tree, which is the input of semantic analysis. Parse tree is the input of semantic analysis. You can assume in this way, like, not assume, actually you can also consider that this set of production rules, the order that it requires to generate this string, is the input to the semantic analysis phase. So semantic analysis know that among these production rules, these are the order by which I should execute to generate this particular string. Now, string generation is not only important. Important is that I have to ultimately evaluate this string, because A is a variable in my program maybe, but A has a value, say 10, B has a value, say 20. So that means, as soon as, for example, in the fourth step you are reducing this E plus T to capital E in opposite way, we should say, we can understand one thing, that something should be added, and that result should get stored somewhere. Now where this particular rule is written, that means somewhere I must have I must have write these rules for the additions, for storing something in temporary variable or something like that, somewhere within the grammar itself. And that is the phase, that is the play, that is the you know the tool present within this semantic analysis phase. So what this semantic analysis actually give the output? What I can say, annotate parse tree. What does it mean? Annotate parse tree means a parse tree which is semantically verified, as well as the output also, you know the rules are somehow is imposed over there, so that in future when we will go for code generation stage, or maybe intermediate code generation stage, or something like that, for three address code stage, at the latter stage, for evaluating the instruction that I require, it become easier. And from this point, the concept of syntax directed definition came. So what is syntax directed definition? Let's try to start with this point from this semantic analysis phase, that is syntax directed definition, or in a simple way we call it SDD. Okay. Now what is syntax related definition? So let's write it a little bit, then I will tell you that SDD is a context free grammar together with attributes and rule. Okay. Attributes are associated with grammar symbols and rules are associated with productions. Now you see, obviously some part is not clear over here. Maybe, for example, what is attribute and what is rule. It will be very much clear very in near future. So, but before that, let's take an example to express this. So, let's take an example that if X is a symbol means non-terminal, okay, and A is one of the attributes, then we write X dot A to denote the value of A at a particular parse tree node labeled as X. I hope now the concept of attribute is a little bit clear. What I mean that means till now we are talking about a parse tree something like this. For example, I have a parse tree something like For example, if I have a grammar like x to y b, something like this. Okay. So what does it mean? Mean I can represent x as y followed by a b, and your parse tree will, parsing will start from in this direction, right? In this direction, in this direction. And now question is that this x is what your symbol. Under this symbol in a represents a value where basically your result of this yb will get stored. I'm assuming that there is some operation representing this yb, and after this operation the value will get stored within as a, as a that we represent by x dot a. So here that is why we call a as an attribute. Okay. So basically what we are giving an informal, not informal, I should say a formal, definition of exactly how the rule of the parse tree will be act on, rule of, how a rule can act on a particular parse tree, right? So you see that, so this is what is a syntax directed definition. Now there is one more thing that we call syntax directed translation. Okay, what we call, this refers to the translation of a string into array of actions. That mean, what you can say over here. So we have one more thing. Let's write it here. That is syntax directed translation, on it is say SDT. Okay, and this is what say that it is basically SDT is and SDT is how we can define uh, the translation of a string into a array of actions. The translation of a string into an array of actions. Okay, so what does it mean? You see, translation of a string. What string? For example, you can take a situation like this. Like if I have a string, say string W, something like this, as I told you that A plus B multiplied by C. If this is my string, then this std represents what should be the array of actions. What does it mean? What does it mean? That means there I have to multiply this B and C first. Whatever result of this should be added with this result, should be added with, the result should be added with this A, and as a whole we will get the final result. Right. So these are the array of actions that we have, and that actually is, represents by this syntax directed translation. So remember, that means one thing is clear, that this syntax directed translation and syntax directed definition are closely related with each other. because SDD represents this symbols. SDD represents, in a particular production rule, SDD represents the grammar with the attributes and rules, and SDT says that what should be the array of actions. But this array of actions definitely depends on these rules, right? So that means, in other words, also you can say that an SDT, we can say that SDT equal to, you can say, grammar added with semantic rule, or the SDT. Okay, so we will see how we can actually generate different type of SDT for a particular for any grammar in a language. For example, let's take an example here. The example can be something like, if I have grammar something like this, that E dash written as E plus T. This is my uh, production rule, right? And the rule actually written in a double, in a closing brace, in a second, within second bracket. How we do this? We write that something like this. Say E dot code equal to, not E dot code, E dash dot code equal to E dot code plus T dot code. So what does it mean? Mean that when you will define the, you define a syntax parse tree for this particular production rule, it will be something like what? It will be something like this. Like I have E dash written as E plus T, right? Now when the parsing will start, actually traversing this tree will start from this root, it will be done in this fashion, right? And it will go and we'll see the leaf and we'll start upward, and at this point, this, when reduction start, it will see what is the value of the code. I mean, the value of code in this point, say E dot code equal to 2. So that will be kept in the memory somehow, and then the traversing continue, and when it will reach, it will also store this T dot code as, say, for example, 3. Now when it will reach to the root again, what will happen? Naturally, this particular production will fire. Production will fire means this production rule will start working, and at this point it's given in the rule that whatever value of the code presented in the node E and whatever the value of the code presented in node T in the parse tree should be added and stored in the code of the node E dash. So you must have a code over here, another attribute code over here, which will basically add the code of this two other nodes, that is 2 and 3 will be added, and result will get stored over here as 5. and this is what represented in a form of rule, that is basically we call, as a whole we call syntax directed translation. So this is all about the basic idea of syntax directed translation, and now we will see that how we can generate different SDT for different type of grammar depends on our requirement.